In this video, I'm going to be introducing you to rotational motion and how to solve a rotational motion problem. So at this point, you're probably pretty familiar with translational motion and some basic kinematics. So if you take a look at our table, we have a delta S, which is very similar to a delta X. Delta S is the change in the arc length. So the amount of meters you sweep through within a circle, that would be measured in meters. We have velocity is how many meters it's traveling per second. The acceleration, the change in meters per second, which is meters per second squared. We have the time in seconds, force in newtons, and mass in kilograms. Now, taking a look at all the angular quantities, they're very similar, but obviously some major differences there. So we have a delta theta, which is in radians. We put RAD, short for radians. If you're not familiar with a radian, I drew up a little diagram over here, and a radian is the ratio between the arc length and the radius. So it's basically taking a look at the amount of circle that's you're sweeping through and dividing it by the radius. And anytime you complete a full circle and you divide it by the radius, it always comes out to 2 pi. So it's basically telling you how much of a circle you're sweeping through. We have omega, which is how many radians you're rotating through per second. We have alpha, which is the amount of radians per second is changing per second. So that's radians per second squared. Time is still in seconds. We have torque, that's in Newton meters, which is basically just a force that's causing something to twist or rotate. And then we have I, which is the rotational inertia or a moment of inertia, that's in kilogram meters squared. So basically what you're doing is you're taking your kinematic formulas and you're replacing it with all the angular quantities. So a lot of it is similar to just regular translational kinematics, but just with some slightly different variables and units. So let's go ahead and try a problem. This problem on the right over here says, a carpenter cuts a piece of wood with a high-powered circular saw. The saw blade accelerates from rest with an angular acceleration of 14 radians per second squared to a maximum speed of 15,000 revolutions per minute. Now we're going to be solving for 3 different things. Number 1, time to reach the maximum speed. So we have a couple variables that we want to go ahead and label. We have the initial angular velocity, which is 0, because it's saying it's starting from rest. We have an angular acceleration, the alpha, 14 radians per second squared. And then we also have the maximum speed, which is basically our final speed. So it is our omega f, our final angular velocity, but it's not in the unit that we want it in, because we want it in radians per second. That's the standard unit. So we're going to take that 15,000 revolutions per minute and go ahead and do a little conversion. So we know that each of those revolutions is 2 pi, as mentioned before, and each of those minutes is 60 seconds. So if you go ahead and take 15,000 times 2 pi, divide it by 60 seconds, then you get a number that is 1,570.8 radians per second. All right, so we got all of our variables, our known variables, labeled with the correct units. So if we're looking for a time, we would use the formula omega f minus omega I over t equals acceleration, the alpha. So we know all of our variables, so we're going to go ahead and plug all those in and then use a little bit of algebra to solve for our t. All right, so I went ahead and plugged in all my variables. I have 1570.8 minus 0 over t equals 14. All I did is cross multiply the t and the 14, and I have a time of 112.2 seconds. So we have our first answer right over here. And number 2, the revolutions completed. So how many revolutions did it complete in that 112.2 seconds? So we can go ahead and use another familiar looking kinematic formula and change it up. And that one would now look like this. Delta theta equals the initial angular velocity times time plus 1/2 alpha t squared. So I know that my omega I is 0, so I can go ahead and cross that out because I know that value is going to be 0. So it's really just going to be 1/2 times my alpha times t squared. All right, so I'm going to go ahead and calculate that and then do one final step to convert that into revolutions. So I went ahead and multiplied by 1/2 times 14 times 112.2 squared, and I got 88,121.9 radians. And the question was asking how many revolutions were completed. So what I want to do is do a little conversion. And I know that there's 2 pi radians per 1 revolution. So I basically just took my answer, divided by 2 pi, and I get 14,025 revolutions. And I went ahead and put that final answer right up there. All right, now for our final one, number 3, what's your angular acceleration to stop in 0.3 seconds? So a lot of times these saws have a safety mechanism that turns them off pretty quickly. So for this one, we're not really going to be able to use some of the same variables that we used originally. So we're not going to be able to use the omega I because it's not starting from rest. We are going to use the 1570.8, but we're going to use that as our omega I. Because our scenario is starting from that maximum speed and then coming to rest. So our new omega F is 0. And the time it's taking to stop is 0.3 seconds. So we can go ahead and use the same formula we used earlier, which is this one right over here, and plug those numbers in to get our final alpha value. Okay, so I got a final answer of negative 5,236 radians per second squared using these 3 values. I noticed this one was in meters. This is actually radians per second. So let me just go ahead and change that. But I just subtracted the 2, which would leave me a negative omega value divided by 0.3. And then it's going to slow it down at this really, really high rate so that it stops at 0.3 seconds. So I hope that was helpful in helping you understand the similarities and differences between translational motion and angular motion, along with how to calculate the values. One more thing to keep in mind that wasn't applicable in this particular problem is that with angular acceleration, there are positive and negative directions. So typically with translational motion, there would be some sort of forward and backwards. So right would be positive, left would be negative, or something like up would be positive, down would be negative. For angular velocities, rotating this way counterclockwise would be positive, and then rotating this way clockwise would be negative. So if it's rotating this way from the first, second, third to fourth quadrant, that's considered a positive omega value. And then the other way around is going to be negative. Like I said, didn't really apply to this particular question, but maybe something that you need to know to solve for other problems. So thank you very much for watching and listening.